Hello everyone, this is Ruby. Today we're going to talk about hypothesis testing two-tailed. So what we're interested in here is a particular research question, and we want to know whether or not online instruction is effective. To evaluate whether or not online instruction is effective, we're going to take a random sample of 36 students, and we're going to place them in an online version of a traditional face-to-face class in mathematics. And so what we're looking here for is, in this problem, the information that we need. So the first thing we would need to do in order to do our z-test is we need an n. So we see that n equals 36. That's 36 students are placed in the online version of the class. The second thing we need is the sample mean. We see the sample mean is 76. The third thing that we would need is the population. And so the population average is 71. We also would need to know the population standard deviation, which is 18. And we would need to know if it's a one or two-tailed test, and what the alpha level is, and the alpha is given at 0.05. And the reason we know it's a two-tailed test, although this will always be given to you, is because we're just evaluating the effectiveness of online instruction. We're not saying whether we think people will do better or whether people will do worse. So the first step that we always do in hypothesis testing is we go ahead and we demarcate out the null hypothesis. And remember, the null hypothesis means that nothing's happening. Remembering that the null hypothesis should always be written around the population mean. So mu of supplement equals 71. The alternative would be that the mu of supplement does not equal 71. And remember, whenever you're doing a two-tailed test, that you have equals and does not equal are what is used to identify the hypotheses. Okay, then the next thing you're going to do is you're going to need to identify the critical z and the statistical significance regions. So we use the following information. We know we have a two-tailed test. We know that alpha equals 0.05. And since it is 0.05, we do know that we're going to take that alpha and we're going to divide it by 2. So we get 0.025. And then what we're going to have to do is find what is the z-score that's associated with 0.025. So we look in our z-table in the tail column for the proportion of 0.025, and we look to find the z-value that corresponds with that proportion. So when we go to our z-table, what we would be looking for is in our column table, which is column C as in canary, which is our third column, we're going to be looking for 0.025. And we see it right there that 0.025 is associated with a z of 1.96. Now remember, this is two-tailed. So on the positive side, it will be 1.96, and on the negative side, it will be 0.196. All right, so then what we're going to do is we're going to go ahead and draw this out for you. You don't have to draw it out in every problem, but just so that you can see what we've done here. So we know we have two tails. So one tail in the positive direction, which is a z of 1.96, one tail in the negative direction, which is negative 1.96. And so what we know is that the critical values are going to be the areas that are green. So to have statistical significance, you're going to have either a value that you've computed of z that is greater than 1.96 or a value that's less than negative 1.96 to have statistical significance. If the value does not fall into either of those ranges, then it would not be statistically significant. All right, so then we get to our third step, which is the easy step, which you know how to do, which is to compute the z. So remember that the z is merely taking our sample mean minus our population mean over the standard error. And remember that the standard error is the standard deviation that's divided by the square root of our sample size. So in this particular case, we have that our standard error, we were given our standard deviation for the population as 18, and we were also given that we had a sample size of 36. So we take 18, then we take the square root of 36, which is 6. We have 18 divided by 6, which gives us 3. Now, for z computed, we're going to do our z-score, which is the sample mean minus the population mean over the standard error. So we have 76 minus 71 divided by 3, which is 5 divided by 3, which gives us 1.67. So if we look back up here, we'll see that 1.67 clearly does not land in the green area because 1.67 is not larger than 1.96, but it's less than 1.96. So 1.67 would mean that we do not have statistical significance in this example. All right, now go to our last page. Our last page is step 4, 5, and 6. So step 4 is asking us for a statistical decision. So the z computed is 1.67, which is not greater than the critical value of 1.96. So we do not have statistical significance. So our conclusion would be that we do not reject the null hypothesis because we did not find evidence to say that this was false, and we do not reject the alternative hypothesis because we did not find evidence to say this is true. Our findings described in words would be: we did not find a statistically significant difference in the final exam grade for those who taught online versus those taught face-to-face. So there appears to be no difference, according to this particular study, if you were taught online versus taught face-to-face. Then we go ahead and compute Cohen's d. So Cohen's d, remember, is our effect size. So how large is our effect? Well, in order to do this, we take away n. So we're just looking at now the sample mean minus the population mean divided by the variability, because what we know is that n can be used to manipulate it, treatment effect. So we're going to get rid of n. So we have 76 minus 71 divided by 18, which equals 5 over 18, which gives us 0.27, which is a very small effect. So if we recall that 0.2 was a small effect, 0.5 was a medium effect, and 0.8 was a large effect. So this would be a small effect. All right, thank you. Bye-bye.